Morning. So, do you want to review?
Yeah.
Exam is Wednesday. Is that correct? Unless you want to take it early, in which case it's Friday at what time? 11, something like that?
We haven't really decided yet, but whenever we should have it
Whenever you get in? Okay,
in. So probably like 10.
fair enough. If you want to take it Friday, you need to figure out when they're doing it. Not my problem. Okay? So am I teaching or reviewing? Okay, you know how that works, right? You run out of questions and I leave. I guess I could teach then. So.
The exam on Wednesday, is that just regular class time or?
Yes. I don't care how long you take, although this room may be used afterwards, so if you need more time than you have, then you can go in the conference room, my conference room here, which isn't my conference room, you get the idea. Okay? Yes.
Can we go over the equations you're going to want us to know? Like calculations?
What calculations do you think you should know?
You know,
Oh, you need to go over that?
not that, but there's.
Well, it was like unison. Did you practice this earlier? You math. It's impressive.
LOI.
LOI? Okay,
Are we going to need to know the math reports method?
absolutely. The equations are not that, there's not equations per se, right? But you want to do LOI? LOI is a rule of mixtures based on mass. Fraction of kaolinite times the LOI of kaolinite plus the fraction of quartz times the LOI of quartz. And then we can continue, right? But we don't typically. Fair enough? So you can continue this, but what else do you have as impurities in the system? Okay, organics. Well, I was hoping not to go to organics, but yes, organics. If you do organics, then you can add that term. What's the level of organics that we would expect in a clay?
1 or 2%.
Not even that much. Small, right? If you wanted to know the organic level in the clay, how might you do it? There are 2 ways, 3 ways maybe, but 2 ways reasonably.
Burn it off.
Okay, you can burn it off. How would you do that?
Well, you would measure it before dry, and you would get it to a point where you know the organics would burn off.
Which would be where? What temperature do you think the organics are gone by? Say again? Yeah, but that's a little hot. Why don't I want to go to 800?
The water was
Because I'm going to burn off the water. It's in the structure of the kaolinite, right? So then the organic and the LOI of the clay is combined together. So where do organics burn? I said at conference once and said, what about organics? I said, well, we look at organics as something to burn off, which she didn't really like that because they were polymer people. But what temperature do polymers burn off? 300, 400, something like that. What temperature must you stay below? 500, let's say 500 to be safe, right? Because dehydroxylation of clay is between 500 and 600 typically, right? So if you exceed that temperature, you have a problem because you're going to start losing water out of the clay structure. Let's see. So here, this is the clay characterization stuff. And here's your TGA curve, right? So if you look at 500 here, you're in the loss of the clay. Does that make sense? So you know TGA is thermogravimetric analysis. It's weight loss as a function of temperature. So typically when we do these, we keep them pretty fast, okay? We do that because we're interested in getting thermal analysis data, which is reactions that occur So the faster that you go, the more intense these reactions are. So you get more well-defined peaks. Make sense? If you go really slowly, it's not very energetic, and then you end up with shallow peaks that are hard to detect. So we typically go fast. Okay? There's a potential for thermal lag, so we keep the sample small. So if you look here, you look about this point where this starts to decompose, 350 is about your limit, which is reasonable for burning off organics, about 350. So if you did that, look at the weight loss to 350, or mass loss to 350, that would tell you the organic matter. And then you have to dry the clay first, right? You know why clay picks up water? What a great question. Pore size is small enough, you'll condense water out of the atmosphere. So when you buy that new computer that has a little silica gel pack in it, right? That's a very fine pore structure material that's designed to automatically absorb water below a certain humidity level, above a certain humidity level, right? I call that a passive humidity control device. Clays do the same thing, but not all clays. And so what happens is in the pores between the clay particles, you'll condense water, given a certain humidity. And I had a senior thesis student several years ago do this project, and he looked at several different clays, not as many as I would have liked, but nonetheless, some clays behave better than others in terms of picking up moisture. Good? So you have to heat it up, and you take it up to, 100 degrees C, something like that. 110, you dry it, and that water comes out. Okay? And then, that mass, and then you go to 300, okay? And 300, you look at the mass loss, that would give you organic. Or you can do this, TGA. TGA would tell you also. But if you look at that curve, there's a little bit of loss that's associated with water at the beginning, and then it's pretty flat. So I would argue for these two clays, there's no organic to speak of. Fair enough? Okay. There's a third way to do it, which is more complex, which is a chemical method, where you can absorb you can react the clay to the humic acid or valeric acid, something like that. It will be, you can dissolve it out of the clay. Don't care. So I'm going to move away from organic as a contribution here. What else do we have? There's two other big impurities.
I was going to say impurities like titanium, iron.
Titanium and iron, those are our big ones. Okay. Now you have other minerals that are in there, but you can't differentiate those easily. You look at this curve, there's no real evidence of other minerals either. Okay, because that's like pretty much perfect TGA curve for a clay, for a kaolinite. Pretty much perfect. Okay. Even down to the point where your weight loss is roughly 14%, which is perfect. Okay. This equals then the LOI of the clay. LOI of quartz is 0. That means the fraction of kaolinite is equal to the LOI of the clay divided by the LOI of kaolinite. And the fraction of quartz is equal to 1 minus the fraction of kaolinite. Good? I'm not real big on memorizing equations, as you should know. Because invariably, you'll forget something and then you have a problem. You don't need an equation here other than, if you can't remember the Rule mixtures equation, we have a separate issue. Yes,
Can you do a free quartz calculation?
I just did it. Look how fast I am. You want to do it from a standpoint of chemical analysis? How do you do it from chemical analysis? Say again.
You first find the moles of
Okay, why?
because it's the moles of silica is what you're going to find next, and that's 2 times the moles of silica.
Right, because you have kaolinite, it's this. One mole of alumina is 2 moles of silica. And so in clays, you almost always have excess silica. you never have excess alumina. You really do not ever have excess alumina. There is a case, but you don't worry about that. So what you have is that if you sort of, it's interesting, how do we get clays, is that we decompose feldspar, okay, by weathering, right? Water comes in, dissolves the alkali out of the feldspar, and when it does that, it destabilizes that feldspar structure. Alumina and silica then are essentially in solution, and they precipitate out as this hydrated mineral that is clay, okay? There are conditions, that progression is predicted to go to 2-to-1 sheet silicates. You don't care about this, but it's interesting, to 1-to-1, to eventually you could get to gibbsite. And so the argument is that the bauxite deposits in general are actually just a progression along this line. And Tom Dombrowski predicts that this is what happens in terms of, not that he's the definitive guy about it, but that eventually the silica is what's soluble in the system and the alumina is not, typically, as soluble. You don't really care about that. There are conditions where you get clay plus gibbsite. We don't care about that. Okay. Typically, you have clay plus quartz. You always have excess silica in the system. And if you have montmorillonites or smectites, you have excess silica in the system. You're interested in excess silica. So you look at the chemical analysis of the raw material. I probably shouldn't open up the thing that says midterm 1's 411, should I? That would be probably poor form. Let's do this. You get to see that on Wednesday. There it is again. There's a lot of those. Here.
Will we get the take-home part of the exam when we take the exam?
I was going to give it to you today. I just forgot.
Right, okay.
If you want to stop by the office, you can get the take-home part today. Unless I can send it to the printer now. I wonder if I can do that. Here we go. All right. So, from the chemical analysis, right? Let's see if I have access to the printers. No. I could add a printer, but that's way too much work. So I could email it to Krishna, but she's not here yet. Yes, I'm feeling a bit. Here we go. All right. How do you do it? Ian? Pick one. Fine? Oh, let's pick a different one. We could do EPK, but I mean, let's pick one that's interesting because EPK has almost no free quartz. So you do the analysis and you come back with a negative answer or whatever. It's confusing. Wouldn't you agree? Really simple. What do you do? Oh, I get it. Oh, my number 4. That'll work. Okay. So Thomasina, I don't know how to butcher her other name. Tomer. She suggested that you take the alumina level, divide by the molecular weight of alumina. That gives you the moles of alumina. All right. So your alumina level, you're at 35.46 divided by 102 gives me what? 0.31.
Yeah.
Cool. That means my silica level on a mole basis is 0.62 times 60. What? Times 60?
Oh,
It'd be something around 40.
37.95.
37. And I have 49.44 divided by minus, excuse me, 37.95. Do that one.
11.49.
11 what?
11.49.
Good.
You have to correct for that it's not 100 grams. It's like, I don't know what else is right now, it's, I just had to assume 100 grams of material in total, and adds up to 85 or 80.
Yeah, I took the LOI already out, right? So you're doing the moles, and you have the moles of silica left over. Yes, you can correct for your, so based on the clay, right? So if you heat treat the clay, then this based on the, how much you get then. So if you divide this by 80, what is it, 84%, it gives you the percent of free quartz in the clay. Good? Is that all right? Yes.
What is the reason behind why people think that you like take quartz out of it?
I just took that exam question off. Because I didn't think we talked about it enough. Okay. It's a great question. Okay, so here's what happens. Wait, I have another one too. There are two things going on. Okay. So when you heat up quartz, okay, alpha quartz on heating goes to beta quartz. This is a, what kind of a transformation? Rapid and reversible. And it happens at 573 on the dot. In fact, it was at one point used as a calibration value for thermal analysis because it is energetic and it is easy to detect, etc. And so the quartz inversion, as it's called. All right. So what's the problem? This change, which is due to a change in silicon to oxygen to silicon bond angle, which I think is around 108, something like that, goes to this 180, and that causes a volumetric expansion, approximately 4% by volume. Okay. The problem is on cooling, it goes through that transformation back. It goes through a volumetric contraction on cooling. So what happens is that quartz particle, which is in the matrix then, and draw it any way you want, but so you have a quartz particle in the matrix, and on cooling, it contracts from the matrix, and it contracts a lot. And that is, what we have here is, this is a little bit idealized, but it's actually from real data, okay? And so there is a lag here because of thermal conductivity, right? So the outside of that crystal reached temperature before the inside. So if you look at this curve for real, and you have temperature, and you have delta L over L, that's expansion. It comes up and it does actually a curve here like that, and then it decreases. So beta quartz has a negative thermal expansion coefficient. As you heat it, it contracts. Okay? But what happens is, on cooling then, when you hit the quartz inversion, it volumetrically contracts. So what you get is CTE of the particle, CTE of quartz, is significantly greater than the CTE of the matrix glass. Okay? So that creates stress in the particle. Now, what happens is that is misinterpreted. So what you'll see is that so you have two cases. CTE of the particle is greater than CTE of the matrix. CTE of the particle is less than CTE of the matrix. Okay? So if the CTE of the particle is greater than the matrix, then what happens is you get tension, okay? You get radial tension, and you get tangential compression. All right? In this case, where the CTE of the particle is less than CTE of the matrix, you get tangential tension, and you get radial compression. So it reverses that state of stress. You could argue that the case on the right, is the case for beta quartz in the matrix. Has to be. Then as you go through the quartz inversion, it inverts, it changes that state of stress. Now the thing about this that is so confusing to people is that when you look at microstructures of porcelains, we see an interesting artifact of that phenomena, which has led people in the wrong direction. There's that one I want. This one. Okay, so I have others. But what you get on, I have another. I'm not gonna do it. What you get on, actually, a great one, comes to think of it. So Max, if you remember Max, he, let's see, failure analysis. Let's see if that one has it. He looked at the fracture behavior of porcelain. And, that's a great image. Here it is. Okay? So, what you see here is, I just drew this for you. The thermal expansion coefficient of the particle is greater than that of the matrix. And here the thermal expansion coefficient of the particle is less than the matrix. So you have compression, radial compression, tangential compression, radial tension across the particle, and then it's reversed here. And so what happens though is that this crack is deflected by these compression regions around the particle. So what you get around the particle essentially is you have compression like this around the particle, which essentially shields that particle. So when a crack comes through, it gets deflected around that particle. This is absolutely true. If you have created radial tension, then what happens is that in this region around the particle, there is tension, so the crack propagates through the particle. Now, what you would predict is that this second case, this connect the dots thing, right, may mean that the particles could interact with each other in the matrix to actually create failure and stress, residual stress that would lead to premature failure or lower strength failure. Davidge is, can you remember his first name? He wrote a book called Mechanical Behavior of Ceramics, which is absolutely brilliant. Okay, and it's out of print. You can still find it in places. But he shows this effect. What's interesting is that when they do the measurements of strength, there is no difference. You got to keep that in mind. Okay, there's a lot of push. There was push for years on particulate composites, putting particles in with different thermal expansion, etc., to create an improvement in strength or toughness. It doesn't work typically. Okay, you give up in one case, you gain back in another. There's not a benefit, as far as we can tell. The benefit is increase in elastic modulus drives up the strength. Okay, so you have this relate. Well, we'll come back to that. So when Max did his samples, he sees this etching. He etches a sample, and what you see in this image, this is a quartz particle here. Okay, and around that particle, you're getting cracking. So you actually, in this case, you create a crack around the particle in the glass. That is called an artifact. What does that mean? What is an artifact? It's how you conducted the experiment. So what does that mean? Well, what we found is that quartz particles are stressed in the matrix. But this quartz particle that you see here, one with a little red dot on it, is arguably just under 10 microns. That is too small to fail. You know how banks are too big to fail? This is too small to fail, okay? And so we have another case. Brian Pinto, years ago, did really brilliant work. Let's see if I can find it. I don't think I have it. Do I? I have it. Maybe I have his PhD. I do. I just have his PhD. All right, never mind. Wait, I do have it. So Brian did measurements. He did direct measurements of strain in quartz grains, and he did it by X-ray diffraction. Okay, and what he found, PhD defense. Look at that. Let's see what else I have. Hang on, I'm gonna look one more place. What he found is that quartz particles will spontaneously crack in the matrix. Okay, now I don't mean to be off on a tangent here, but the issue is, there is quartz. It does not affect the strength. So everyone, because they look at the microstructures, so here, for example, these are really small particles. There's a 10 micron size bar. Notice that you have, was there a moment ago? Let's go this way. Better? Better. Okay, if you look here, this is a quartz grain, this is a quartz grain, this is a quartz grain, etc. Good? Okay. See the cracking here that goes through the quartz grain, comes back out and around? Okay. So the quartz grain, turns out that in order to crack in the matrix is actually significantly stronger than the quartz grain. Cracking doesn't occur in the matrix. So the quartz grain will crack. So what? Right? It's protected by this compressive zone. But when people look at the microstructures and then they over-etch those microstructures, they end up with big crevasses around the quartz grains. And when they get those, they decide that the quartz grains are responsible for strength. Does that make sense? Okay. So then they go to efforts to remove, sometimes heroic efforts to remove quartz from the system. So what you have is a quartz particle, and you have what's called a dissolution rim. And what happens is that the quartz particle dissolves, okay, and it pulls away from the molite needles, if you will. And since you're not oversaturated or saturated with alumina in this region, you end up with a quartz dissolution rim, which you see clearly in the image. Let's see where it goes here. We don't see it here. This is unetched. If you etched it, you'll see it. So when we polish, we create stresses that cause the grains to fail. When we etch, we preferentially etch. So Max ended up with this really spectacular piece of result, a piece of data. First, by the way, this is the matrix situation for quartz, okay? And then what you get is you have 4 choices for what can happen. Either you crack through the particle, that's A, or you crack around the particle. So essentially you can crack through the particle, right? You can crack on the peripheral of the particle. Makes sense? In the particle, you can have these two connect, that's C, or you could crack out here, right, in the glass. Turns out that you don't, right? And we can demonstrate that, and Brian, in fact, did demonstrate that. This is more common. Your greatest tensile stress will be on some axis that's based on the highest thermal expansion coefficient along that crystallographic axis. And as you may remember, quartz is anisotropic. So it has huge difference in thermal expansion coefficient based on one crystallographic orientation over another. That means there's a preferred crack direction. Okay? And we actually see that. And so depending on the thermal expansion orientation, and then the particle will crack perpendicular to that highest thermal expansion coefficient. Why doesn't it crack in the matrix? Because it turns out that you could argue that the glass, pristine glass, is extremely strong. We've all had glass, right? Okay? You know that glass in pristine condition is extremely strong. How do they measure this? They take little glass fibers and they measure them liquid nitrogen temperatures in the absence of any humidity, right? And they get 11 gigapascals strength out of glass. In the middle of that porcelain, you would expect it to be pristine. There's no chance for humidity to get into that sample. Humidity is on the exterior surface. It's not porous, it's dense. You have a quartz grain in the glass matrix. The glass matrix is hugely stronger. But in this case, for quartz, it's a factor of 5 stronger than the quartz grain. And for aluminum, it's a factor of 2. Okay? And so we actually will crack alumina grains in the matrix before the matrix fails. And Brian's data is here, which I don't think we talked about. Have we shown this data yet? So this is not on the exam. I took this question off the exam because I didn't think we talked about it. Okay, here's what happens. Quartz particle size on the x-axis versus lattice strain, which by the way is off by a factor of, it's off by a factor of 100. I think it's an error in this slide. Goes across, here you are, this is 10 microns, 20 microns, 30 microns. So you have 30 micron quartz grains, there's almost no residual strain, and then it comes up. And then what happens here? Why does it come to a peak and then decrease? Ian? Adam? Why does it crack? Jill? Quartz grains spontaneously crack in the matrix when you exceed the strain of failure. So quartz grains get big enough, they crack in the matrix on the cooling cycle. Okay? And then it comes down. The interesting thing is, you can calculate the principal stresses in different directions. If I put alumina particles in, this is alumina particles, they're the closed inverted black triangles. Okay? Look, they fail also. Large alumina grains. So quartz grains somewhere around 90 microns will spontaneously fail in the matrix. Alumina grains somewhere around 120 microns will spontaneously fail in the matrix. Okay? I have a difference in failure strain. What does that mean? Yeah, but alumina doesn't have that transformation right. It just has a higher thermal expansion coefficient. What does it mean for the failure strain for the two particles to not be the same value? So, yes?
One will always crack first.
Which cracks first? Wait a second, let's take a step back. Where are the particles? What are the particles in? What matrix? It's not a trick question. The glass, right? If the glass is failing, what would you expect? That the strain and failure would be the same, wouldn't you? If I put two particles in the glass and the glass cracks, my strain at failure would be the same. Does that make sense? Everybody? I mean, this is a huge deal, right? We put two particles in the matrix. They do not fail at the same strain. That means the failure could not have been in the glass. You understand? The cracking could not have occurred in the glass. The cracking had to have occurred within the particle. Is that like the coolest thing ever? Maybe not ever, but it's up there, right? So the particles fail in the matrix. And then here's the problem. This is what, let's get out of here. Go back to Max for a second. He found something that's not a surprise necessarily, but is really awesome. He etched the sample. So there's a bunch of stuff about etching that we're dealing with, and it's right here. He etched porcelain samples in contact with the glaze. The glaze is in compression, the porcelain body is in tension. What you see is that in the light etch, this is light etch. The light etch shows the cracks up around the quartz grains because the glass is in tension around the quartz grain. The glass is in tension this way, right? So when I etch, because I'm pulling on the glass, it preferentially etches where the glass is in tension, right? So when I etch this, I get a crack in the glass, not in the quartz, because the quartz is really not that soluble in HF, but the glass is highly soluble in HF. But where I have tensile strain in the system, it will preferentially etch. Make sense? You may have actually talked about that in glass. If you, when you do mechanical testing of glass, right, in humidity, that tensile surface is reacting with the atmosphere, and it causes a reduction in the strength of the glass, right? Because it will preferentially impact where you have tension. What you have here is, this is the glaze, this is the body, and the body preferentially etches at the body-glaze interface because the glaze is in compression and the body is in tension only at this region. So it preferentially etches here. You can see the range of how much tensile strain is left in the body. That's cool. Okay. And so here, when we etch this, we get etching around the quartz grains. You see the cracking around the quartz grains, but not within the quartz grains. And if I polish the sample, depending on how well I polish or how energetic I am in polishing, I can damage those quartz grains and they show up as crack. So why is quartz a problem? Is because people look at microstructures and they see this and they're worried that this compression, this crack in the quartz grain is going to cause these cracks to connect the dots, and it cannot happen. See, so this is a little isolated crack in the system. Don't care, right? And but if I had particles like this, it might make a difference, but we find that it doesn't. So the bottom line is that because of microstructure evidence and because of the quartz inversion, everybody gets so excited about that, okay, I can, the argument is that quartz is leading to failure. Okay? Not the case. Do we need quartz in the body? Yes. Why? And good, it increases viscosity, and the other reason is it's necessary to help make glass, right? Is quartz a good raw material for making glass? Why? Well, yeah, but is there something that helps quartz dissolve into the glass? I should have thought of this before I wrote the exam. So, why? Why is quartz a better raw material to make glass? JT, why is quartz better as a raw material? It's a lot of silica because it's just silica, right? So what is the benefit of putting quartz in here as a raw material? You're going to heat it up, right? You heat it up to what temperature?
1300.
1300 C, right? You need to know this, by the way. So, alpha quartz, right, goes to beta quartz. I wrote that the other way a second ago. 573. Then what happens? Go to tridymite temperature.
67.
Okay. Oh, you mean that quartz doesn't want to be quartz anymore above 867?
When you pull it back down, it's going to go out.
No, wait a second. Let's go back to here. Okay. I'm talking about what happens in the body. Take the body up to temperature. Quartz then, right, wants to transform to tridymite or cristobalite, but tridymite. Then I go up to here, 1472 goes to beta cristobalite. Right? So I'm firing someplace in here at, say, 1300 degrees C, 1250 to 1300 degrees C. Quartz does not want to be quartz anymore. These transformations that go from quartz to tridymite to cristobalite, they are reconstructive, sluggish, and typically irreversible. But what you need to walk away with is quartz doesn't want to be quartz anymore. It wants to transform to something else. That action, in order to transform to something else, we have to break bonds, silicon-oxygen bonds, and restructure those silicon tetrahedrons into a different network. We go from quartz to tridymite or to cristobalite, And that breaking of bonds facilitates quartz to dissolve into the glass. Does that make sense? You have a driving force for quartz to convert to a glass, actually for the bonds to break. And as those bonds break, you find that silica dissolution into the glass goes up faster. And the experiment that you could do is you could bring in amorphous silica, right? You could bring in fused quartz, if you will, amorphous silica, put that in the porcelain body. What you find is that it doesn't help the glass formation very much. You get more slumping out of a body prepared with amorphous silica than you do out of a body prepared for quartz, because that silica that's in there already as a glass doesn't want to go into the rest of the glass very well. It's quite happy the way that it is. Okay? So quartz is the perfect material because it doesn't want to be quartz anymore at temperature. Does that make sense? Okay, so you put it in there and it's dissolving into the glass. Other questions? Does this answer your question? So don't take quartz out of the body because then the body will slump at temperature. Okay, you need it in there, and it's not controlling the strength. Why does alumina increase the strength in porcelain bodies? It increases the elastic modulus. And it's not because alumina doesn't have a phase transformation. That's the other thing you're reading. Oh, there's no phase transformation. No, it just has a much higher elastic modulus. And elastic modulus follows the rule of mixtures. Right? So the fraction of alumina you put in, you'll increase proportionally the elastic modulus of the body, and that will increase the strength. Good? Yes?
What is a saturated silicate?
A saturated silicate is not on the exam. Saturated silicate is an argument that structurally you cannot stuff any more silicate into that network. And it really has to do with phase diagram argument. I found a nice description of it that I can post to Canvas for you. It's a geology term. So feldspars are saturated silicates. You cannot have more silica in that structure than what you have already. And the way that you might look at that is this way. Let's see, introduction. So if you go to the phase diagram, it's really readily evident in the potassium aluminosilicate phase diagram, better than the others. Here we go. Okay. So what you see here is, we don't see this very often, say like calcium or you see it in sodium, but here you have one potassium, one alumina, one silica. Here's just potassium alumina, so there's no silica here. We go to 1, we go to 2, we go to 4, we go to 6, and there are no more stable compounds above that have more silica in there. So you have saturated that silica. But the argument from a geology standpoint is a little bit different, and it has to do really with how those materials solidify or crystallize out of the melt. But you have a saturated silicate. So where you run into issues is here, lucite, for example, 1 potassium, 1 alumina, 4 silica, is more analogous to nepheline. Okay, so nepheline is a mineral, nepheline cyanide is a rock. And so, but nepheline cyanide is considered a feltrothoid, so it's like feldspar, but it isn't feldspar because it is not a saturated silicate. It's roughly here, okay, for lucite is. So you have a mixture of nepheline and feldspar in nepheline cyanide that gives you a different, gives you less silica per flux or alumina than you have in feldspar. But the composition of nepheline cyanide, the alumina is saturated, but not the silica. Okay, so feldspar is a saturated silicate. Nepheline cyanide is not. Okay, there's still room for silica in that structure. Does that help? Yes.
Are you gonna want us to know the names of the structures?
No.
Or what the
Which ones do you think I would want you to know? Say again. Kale and I, good. How about quartz? If I can't draw quartz, I wouldn't expect you to be able to draw quartz. And if you need that verified, I can't draw quartz, so. Nor can I draw a crystal blade or feldspar, so no, I don't care about that.
What types of things would you want us to know about the structure?
Shared corners, right? You know, I don't know how many questions are on the exam. I could check, but you know, there's a couple questions on structure. There's questions on. There's a couple of UMF questions in there. I don't know. There's stuff about the role of quartz. There's stuff about what were we talking about? What do you think about rheology? We touched on rheology on Monday, right? 5 factors that control suspension rheology? What do you think? I think it's on there.
So it's different points, you gotta put that on there.
Say again?
Those are like easy points, you gotta put that on there.
You know, what's interesting about that is we don't talk about that very much, but there are still students who can't figure that out, and they go in there and write, you know, particle size, surface area. Yeah, particle size is in there, but I mean, they like start thinking too late about the problem. And your goal should be to make this easy to grade. You don't think of it that way, but that's a good goal. Yes. Any questions? Any other questions? Everything is posted, I think, to Canvas. The thing you asked for is posted probably this morning. What was it that you asked for? Things on rheology.
Yeah.
Yeah. So we didn't get into dispersion behavior, so that's not on the exam. Let's see what else is on the exam. I'm not going to show it to you. Not yet. Although I probably could, it wouldn't really make a difference. No, it's pretty easy. So this is set up as a take-home. This is the open notes portion. Typically, you would get it after you do the first part, but it's not complicated. I took out the complicated questions. You have 4 questions to answer, more or less. So it should be straightforward. It's due Monday, a week and a half from now. Okay. Any other questions? Are you good? Yes.
If you ran back to your office, could you print it right now?
Yes. Can I walk back to my office instead? Would that be acceptable?
You can skip.
Not going to skip. Yeah, so if you just stick around for a few minutes, it won't take long to print it, and I'll just double side it, and you'll get this plus the ternary. Okay. Any other questions? It says work in groups of 1 to 3. All right. You can do it by yourself. It doesn't make any difference. You can work with other people. Submission can be via email. Okay, but that's a little bit tricky to plot this, but you can plot it, and you have that app for your phone that scans, tiny scanner, works great. You know, you can do it that way, whatever. Okay, but just email it to me, and then we'll do it that way. Okay. So, are you all meeting right after this to do this part of the exam? Then you're going to say, okay, you 3 do this, you 3 do that. Any other questions? Good? What's that? It's not difficult. Okay? Great. Have a great week and a half. I'm going to. So, not that you care. And I will see you on October 7th if I don't see you in Portland.